material at various levels. So based on the magnification level at which you are looking at the material, you can categorize the internal structure of the material into several classifications. So based on the level, we will classify structure of the material as the macrostructure. This is the structure of the material which you can see without any device, or you can see directly by the eye. And the limit of the resolution of the macrostructure is limited by the resolution of the human eye, which is typically of the order of a fraction of a millimeter. So whenever you are observing material on a length scale of a fraction of a millimeter, that structure is referred as the macrostructure of the material. If you try to further magnify the material surface using an optical microscope, whose typical magnification is around 1500x, what you observe is called the microstructure of the material, where you can see the finer details of the surface of the material. At a later stage, I will quote a couple of examples of the microstructure so that you get better idea what precisely I mean by the microstructure. At this point, microstructure is basically material's internal constituent structure which you are observing typically at a micron length scale, and that is why the name came as the microstructure. If you further magnify the material, the next level of structure will be achieved, which is called the substructure. Now, substructure cannot be seen either by the naked eye or with the help of an optical microscope. You need a more better device which can give you higher magnification as compared to the optical microscope. And one can achieve this with a device which is called electron microscope. Electron microscope possesses much higher magnification as compared to an optical microscope. For example, the quoted magnification for an electron microscope here is 10 to the power 5 times the original magnification. So magnification is 10 to the power 5x. If you compare it with the optical microscope, which was only 1500x. So you can see electron microscope can zoom the material surface to a very large extent as compared to what one can achieve in an optical microscope. And the structure which an electron microscope reveals is called the substructure. Now the question is why optical microscope has a limited magnification and you can overcome that limitation with the electron microscope. It is vis-a-vis to the wavelength of the radiation that you are using. In an optical microscope, we use the visible light as the light source. And you know that the visible light has wavelength that ranges between 400 nanometer to 700 nanometer. So typically the limit of resolution is being defined by the diffraction limit. You know, if your object size is of the order of the wavelength, then the diffraction takes place. So if your object is having a dimension which is equal to lambda, it starts giving you the diffraction and you can no longer image it. So if you are using an optical radiation, visible wavelength, then your smallest possible dimension which you can observe will be equal to the lambda, and that too theoretically. In an actual optical microscope, many other limitation comes from the technical aspect, and typically what you observe is much higher than the limit defined by the lambda. So if I am using the blue color, the minimum size which I can see is around 400 nanometer, which comes out to be 0.4 micron. If you convert nanometer to micrometer, 400 nanometer becomes 0.4 micrometer. So that is the smallest possible dimension you can see under an optical microscope. But such limitation you can overcome in an electron microscope. Why? Because in the quantum mechanics, we have studied that electron, being a very tiny particle, when in motion behaves as the wave, as per the dual nature of the matter. And if a particle behaves as a wave, you can define its wavelength as the de Broglie wavelength, which is h upon p. And p is the momentum, which is equal to mv. Since mass of the electron is constant and Planck's constant is also a universal constant, lambda is equal to h upon p is equal to h upon mv. Now only depends on the velocity value of the electron. And by applying different voltage to an electron, you can either increase or decrease the velocity. That means you can tune the velocity of the electron, and hence you can also tune the wavelength. And that is the precise idea behind an electron microscope. Now you can minimize the wavelength associated with the electron of the order of an angstrom scale. And hence, with an electron microscope, you can magnify the material to an angstrom scale, where you can observe very minute, finer details of the structure of the material, and that structure is called the substructure. So we will frequently refer to the microstructure and substructure in our study. Remember, microstructure has a micron scale, substructure has a submicron scale, typically an angstrom. Microstructure can be revealed with the help of an optical microscope, while substructure can be revealed with an electron microscope. Next in the level of structure is even finer, which is called the crystal structure. Now in our primary school days, we have learned some fundamentals of the crystal structure. Most of the properties of the material depends on the periodic arrangement of the atoms, that too in a definite manner. And that definite organization of atoms' periodicity is being defined in terms of its crystal structure. How one can study the crystal structure? To study the crystal structure, we will going to use an X-ray diffraction technique, and we will going to study the X-ray diffraction technique in detail at a later stage. So you will understand there how exactly an X-ray diffraction will going to give us the crystal structure. The primary idea is again related with the wavelength. You know, if you want to produce diffraction, your diffraction object should meet the wavelength of the radiation, then only diffraction will happen. If you use visible light, the wavelength is very large, like 400 nanometer to 700 nanometer. When you look at the periodicity of the atom, it is much smaller than 400 nanometer, typically of the order of angstrom. So if you want to produce diffraction from atomic planes which are apart by angstrom distance, you need a source whose wavelength is also of the order of angstrom. And that is where the X-ray comes handy, because the X-ray wavelength is typically of the order of couple of angstroms. So one can easily use X-rays to produce diffraction from the periodic arrangement of atoms. And if you study the X-ray diffraction in detail, you can identify the crystal structure of the material. How exactly we will going to produce X-ray diffraction, and from that how one can actually identify the crystal structure, those things we will discuss at a later stage. You can also achieve the same information by an electron diffraction, because electron can also have the similar wavelength which an X-ray has. So you can either study with X-ray diffraction or you can do the same study with the electron diffraction. Next structure in the level of the structure is the electronic structure. Electronic structure we have also studied in +1 and +2 when we used to define the structure of the silicon atom. When you talk about the electronic structure of a material, it is the structure which defines the arrangement of electrons around the nucleus. So whenever you are describing the organization of the electron around the nucleus, the structure that you are referring is the electronic structure. So now you are within an atom. So the length scale that you are discussing will be a fraction of an angstrom. How one can identify which way electron organizes themselves around the nucleus? If you want to study that, you need to use spectroscopic techniques. We will not going to study spectroscopic techniques in this particular course, but if you are interested, you can take an advanced course on spectroscopy where you can learn how one can study the electronic structure. But we have studied in detail how one can approach to an electronic structure from knowing the value of Z, which is the atomic number of the material. So if you know the atomic number, like say sodium, which has Z to be equal to 9, you know the organization of the electron around the nucleus. For Z equal to 9, you have 1s2, 2s2, and 2p5. So that will be the organization of the electrons around the nucleus. Likewise, you can define electronic structure of any material if you know the Z value. The last in the level of structure is called the nuclear structure, where now you enter within the nucleus of the atom and you define the organization of constituent of the nucleus, which is protons and neutrons within the nucleus. How one can get that information? Again, there are set of tools with which one can achieve this information. The tool is called nuclear spectroscopic techniques, or NMR. In this course, again, our focus will not be in the nucleus. So we will no longer further discuss the nuclear structure of the material. If you are interested in understanding the nuclear structure, you have to take an advanced course on nuclear physics. So for us, in this course, we will study in detail the microstructure of the material, the substructure of the material, and crystal structure of the material, and correlate them with the corresponding properties which the material is going to give us. In electronic properties, we will also refer the electronic structure of the material, whose knowledge we are already possessing. Okay, so if I move from a macrostructure to a microstructure to a substructure, what we are changing is the length scale over which I am looking or observing the material. In this particular slide, I have shown a macrostructure, the structure which you can see by a naked eye in the first leftmost diagram, which is an engine block. So the engine block has a bulk dimension which is typically of the order of couple of centimeters by couple of centimeters, and on that I have made a very small square box, And now what I am doing is I am focusing my optical microscope in that small region marked as square where my cursor is there at present, and I am zooming that region under an optical microscope. And what you can see is the second image from the left where my cursor is there at present. So what you can see is some patches in a gray scale where few patches are more dark while few other patches are relatively bright. So if you compare this region with that region which is observed in the first image, your first image is completely white, while if you put it under an optical microscope, part of it is brighter while the part of it is darker. What is the difference between this brighter and darker region? They represent different grain made up of different structures. So the material which was looking to us as an identical material in the macrostructure, when you reveal its microstructure, it gives you a different information. It says material is not made up of a single homogeneous solid, rather than it is made up of patches of materials which has different internal structure. Now what we do further is we take a very small narrow region which is a junction between a dark region and a bright region. You can see the region where my cursor is there at present. Now I am zooming up that very small region further and looking at the substructure. So what I am doing is I am putting that material under an electron microscope and zooming the junction part between a dark region and a relatively bright region. And what you can see is a magnified image which is typically having its dimension from 50 to 500 micrometers, where you can see the granular structure of the material. You can see there are small irregular shaped circular geometries surrounded by dark black lines. These dark black lines represents the boundary of the grain, and the continuous bright patch is the uniform arrangement of the atoms, which we call grains. So the microstructure under a magnified scale reveals the grain structure of the material. At a later stage, when I will start correlating the property of the material, you will see how the size and shape of the grains eventually affects the property of the material. So knowing the grain size and grain distribution will be very, very important in predicting the material's property. How you will do that prediction? I am coming to that point in a moment from now. What we did further is we further enhanced the magnification on a narrow patch which is marked here where my cursor is there, and I have further magnified it, which revealed the structure of the material in the fourth image from the left. What you can see is a continuous patch with some black lines. What are these black lines? Now we are looking at the material on a length scale which is of the order of nanometer. So these line-like structures are basically the defects which are present within the solid. Now compare the fourth image with the first image. First image looks to be a continuous one, a perfect solid, as if it is free from any kind of defect. While the fourth image reveals that the structure of the material possesses some defects. Always remember, every real material do have some defects always present in that. And if you want to define the performance of the material, you should gain good understanding of the defects which is present in the material. So if whenever you want to study defects, you have to have a magnified substructure at couple of nanometer scale. Now coming to the last image, what we did is we take again a very narrow region on the fourth image marked as a square, where my cursor is there at present, and we have further magnified that particular region, which gives me the final figure where you can see a parallel line like structure. You can see there is a line going and another parallel line going. These lines represent the atomic planes. So from a macrostructure to a magnified substructure, what you can reveal is basically the way atom organizes itself within the structure. So if you study these structures at different levels, you get different information about the same material. At microscopic scale, you talk about the granular structure. At substructure, you talk about the defects that is present within the solid. Okay, so now the important question is, what if I know all these things? I take a material, look at the material by a naked eye, then under an optical microscope, then under an electron microscope, and I reveal all those images. And from that, I gain certain information about the internal structure of the material. Then the next question is, how I will going to predict the behavior or property of the material. So to understand how the material will going to behave, we are looking at the mechanical property of two different materials with the same chemical composition but different structures. So you can see there are two images shown. In the left image, you have large size grains present, while the image on the right, you can see large size grains are missing. You have only small size grains present. So the primary difference between the two materials is their grain size. Now, on the right hand side, we have shown two graphs. The upper graph is the tensile strength versus the annealing temperature graph, and on the right hand y-axis scale I have also plotted the ductility. So it's a ductility versus the annealing temperature graph. And in the lower half of the same graph, I have plotted grain size as a function of annealing time. Annealing temperature. So what you can see at the lower graph is, when the annealing temperature increases, your grain size also increases. That means if I process the material at higher temperature, I end up with larger size grain. And if I process the same material at lower temperature, I end up with finer size grains. So how the grain size now affects its tensile strength. So look at the graph of the tensile strength as a function of annealing temperature, or you can say as a function of grain size. What you can see is your tensile strength is maximum when your annealing temperature is lowest, or you can say your grain size is lowest. When you increase the annealing temperature or say grain size, your tensile strength falls, and then it plateaus to a minimum value at larger grain size. Same way, if you look at the ductility graph, the ductility is lowest for these finer grains or say smaller grain size, and when you increase the grain size, your ductility goes up. That means the tensile strength and ductility behaves opposite to each other. with increasing grain size, your tensile strength falls, but your ductility increases. So as a design engineer, now you have to choose an appropriate annealing temperature where you produced an optimum grain size of the material that gives you the required tensile strength and ductility in the material. Remember, you cannot make both the tensile strength and ductility high in one single case. Okay, there is a question. What is annealing temperature? Annealing temperature is basically the processing temperature of the material. Whenever you are making a solid, you always heat that solid, and the temperature at which you are heating the solid is called the annealing temperature, right? So while defining the annealing temperature, which is the processing condition, you are controlling the structure, which is the grain size, and the structure affects your properties, which is tensile strength and ductility. So in this way, you can make the correlation between the processing condition, the structure, and the properties. And once these properties are known, you can define what will be the tensile strength of your finished product, what will be its ductility under the circumstances which you have make your material. So this was one of the example where you can make a good correlation between a structure and the property of the material. Let us look another example. In this particular slide, I have shown 4 microstructures named as A, B, C, and D. I am not describing the difference in the microstructure, but if you see from a layman's perspective, what you can see is the structure of image A is different from structure of image B, is different from the structure of image C, and is different from structure of image D. At least all of you will agree to me that 4 of them are different from each other. What I am showing simultaneously is a graph of hardness versus the cooling rate. Now, what exactly the cooling rate is? Cooling rate is basically when you are making your solid, you are in a molten phase and then you have to cool it to the room temperature. Now, the rate at which you are cooling your molten metal is being defined as the cooling rate. Faster is the cooling rate, finer will be the structure that you are gaining. And smaller is the cooling rate, larger is the structure that you are getting. So what we have is image D is the one which is made at 1000 degrees centigrade per second cooling rate, while image A is the image of a material that is being made at a very slow cooling rate of 0.01 degree centigrade per second. So in what way image A to D differs? They differs in terms of the cooling rate with which the same steel is being made. Now look at its hardness. You can see the hardness of the material in image D is highest, and if you read its magnitude, it is roughly 600 in its scale, which is called BHN. What is BHN? We will talk about it at a later stage. While the material in image A has a much lower hardness, which is slightly above 100. That means the same steel material, if you alter its processing condition, namely the cooling rate, you can either increase or decrease the hardness of the material. And why this is happening? This is happening because at different cooling rates, you end up with different internal microstructure of the material. So at given cooling rate, what kind of microstructure one can produce? If you know that, then you will be able to predict the hardness of the material. Okay, there is another question from Yashika. She is asking with what kind of source we can cool the material with such high cooling rate. Say, I said image D is produced at a cooling rate of 1000 degrees centigrade per second. It's a very, very rapid cooling. So how one can achieve such rapid cooling? Now, mainly in the industry, there are two practices which people follows. One is they quench the solid. What is quenching? Quenching is the molten phase of the liquid metal is suddenly being reduced vis-a-vis to its temperature by dipping it directly into a water. That is one way of doing that. If you want even faster cooling rate, then a chilled water may not be appropriate. In that case, you need a substance whose own temperature is much lower as compared to the room temperature, because water will of course be at the room temperature. So for those kind of things, people uses liquid nitrogen, because liquid nitrogen has its own temperature which is 77 Kelvin. So if you want to achieve cooling rates like 1000 degrees centigrade or tens of thousands of degrees centigrade, then you have to use large quantity of liquid nitrogen, and you suddenly dip your metal into the container of the liquid nitrogen, which abruptly cool it down at a very, very rapid rate. So you can achieve tens of hundreds of degrees centigrade per second cooling rate with the help of liquid nitrogen. My overall point is, if you alter the processing condition, it alters the structure, and if you alter the structure of the material, you can tune the property of the material. In this case, I have shown how you can tune the hardness of the same steel from 100 to 600 on DHN scale. Another example which makes a correlation between the structure of the material and its property can be seen here. You can see there are three tiny pieces of a disc-like geometry of sapphire. Sapphire is basically an ore of alumina, which is called Al2O3. Technically, it is called aluminium oxide. And what we are looking at is the transmission of light that is happening from these three different pieces. What you can see is the first leftmost piece is completely transparent, and you can see the light transmit completely from the first piece of alumina, while the intermediate or second middle piece is semi-transparent. Only fraction of the light can get transmit through the middle disc, and the third one, which is the rightmost disc, looks to be a completely opaque to the transmission of the light. So it's the same material of a same thickness, but the degree of light that is transmitted through them is different. Why it is so? It is because the internal structure of the material in all the three cases is different. The one which looks to be transparent to us, you can easily predict what kind of structure it is possessing. It is possessing a glass-like structure, because glasses are transparent to the visible light, while the semi-solid case is the one which possesses a short range order, or you can say some form of minor ordering, some crystallinity in it, and the one that is on the right hand side possess a completely perfect crystal structure, which we used to call the single crystal. So the leftmost image is, you can say, amorphous, and the rightmost image is single crystal. Again, the question came, how the same material becomes either amorphous or single crystal. So that depends how you are processing it. In general, if your cooling rate is very, very high, you end up with a material that possesses an amorphous structure. And if you are cooling your material very, very slowly while you are making it, you generally end up with a single crystalline material. It's a thumb rule. There are many other conditions which you need to meet while you are making the solid, but the important point in general is the rate of cooling affects the crystal structure, and the crystal structure controls degree of transmission of light which is happening in the material. So what is the overall message? My overall message is, if you want to define the material's behavior, you should be able to make a strong correlation between the structure and property. So throughout this course, we will keep correlating the structure of the material vis-a-vis to the property of its material. So we will going to study this subject in two phases. In the first phase, we will study the structures of the material, and in the second phase, once the knowledge of structure is with us, we will going to correlate the structure with the properties of the material. If you have any questions or queries up to this point, you can raise them. I will be able to answer them at this point for a minute or so. Else we will proceed to the next part, where we will start studying one kind of the structure, the first kind of the structure.
Sir?
Yes?
So what is the relation between hardness and cooling temperature?
If you see that graph, you can see the material which is having, I'm just going to that graph quickly. You can see the graph here. When the cooling rate is high, like say 1000 degrees centigrade per second, you end up with image D, right? 1000 degree correspond to a point that is having image D, and image D corresponds to a very high hardness. That means your cooling rate is high, then your hardness is high. And why it is happening? It is happening because your internal structure gets changed. How the internal structure changes, I will talk at a later stage. We will study those things in detail at a later stage.
Thank you, sir.
We have a lab. Can we leave?
Please mute yourself. Okay, we are about to close. So if there are no further queries, let us close today's discussion so that you can go to next class. From tomorrow onwards, we will start studying our first type of structure. So we are stopping for now.